need you to understand this slide, say even one. See, we have U1 here and Y1 equal to W1 double dot, that's accelerations. Time, we have U1 and Y1 time history. Time history. For 5 seconds. Right? And but U3 we have annoying, that's annoying disturbance. Right? Then from this U1 and Y1 we perform system ID identification to determine observer macro parameters. Alpha 1, alpha 2 to alpha P, and beta 0 and beta 0, beta 1, beta 2 to beta P. Alright? Then compute control parameters, control parameter alpha 1C, alpha 2C to alpha PC and beta 1C, beta 2C to beta PC. Alright? That gives you the control feedback force. Then, so we compute that, use the following the control force equations. That's control, use the control force equation. Alright, this to compute the control force. That's a step. So in this chart, we have 5 seconds input, that's random input, and output Y1, but we don't know this. But this one also excites the system. So the excited the system, we have U1 and U3 to excite the system. But when we do system ID, we just use the input we know, the U1, and the output Y1 we know to compute alpha 1, alpha 2, alpha P to beta 0, beta 1, beta 2, beta p. And then from that, then we compute the control parameters. That's the control parameters. After we control the parameters, then we use the control force equation to compute my feedback force. And that means I turn on this after 5 seconds. And that's the final control responses. So this is the feedback control responses. You can see that after 5 seconds, it's quiet. But if you look at that carefully, from 5 to 15 seconds, they still have the some responses here because your disturbance is still there. You turn on the control feedback, your disturbances, if you look at this, external disturbances from 5 to 15 seconds still here. Okay? So you still, your disturbances never quit. If you don't give them control, then your open loop at 15 seconds can go up to about 200. The unit to about more than 200. But after 5 seconds, if you turn on your controller, even your disturbance is still there, your response is getting close to 0. That means your disturbances, I can almost cancel your disturbances induced responses. Okay, so your disturbance, although the disturbance is still there, my system is unstable, but I can still control. Again, I do not know the external disturbances. I have no measurement about it. Just like in the aircraft, I don't have any measurement from the aerodynamics disturbances. Okay, so this is the procedure to compute this. All right, and this just shows you that the predictive control can work for unstable systems. All right, then after that, those are simulation. After that, we have done the Cobra stick model. That's the helicopter model, and these are real experiments. And let me show you some of the stick model. And the same thing here, we just use about 0.7, 0.6 second data. We have a 0.6 control input data, and also we have responses, accelerated responses. And this Cobra stick model, they also have disturbances. Their disturbances come from this one. This is their disturbances. Well, that's their disturbance. This is like my U3 for this system. All right? And then we have also control force from other places. And exactly the same thing, the GBC is off. That means generalized predictive control off because I need some data for system ID. So the 0.7, about some 0.6 second, that data I use for system ID, but I have less than 0.1 second to do all the computation. So these computations takes less than 1 second, or in that case, take less than 0.1 second. It's very quick because it's only the algebraic, the matrix manipulations. So this take no time to compute those. So for computing this is very quick, very fast. Then after that, we turn on the controller. You can see that after we turn on the controller, about from 0.7 second to 1 second, it's become quiet. Although you still see some responses here, because that disturbance is still on. You still have a disturbance, just like the earthquake is still on. But my 101 is almost quiet because I have the like a TND, on the 101 like that. So disturbance is still on, but you don't feel much. So that's still on, still quiet. That's the stick model. And this one is a simulation, the case we call XV-15T roller, and this is another helicopter plus airplane. This is really this wing here, this propeller here. That look at this. This is like a helicopter, so he can fly vertically, just like a helicopter fly out, and then this one then turn 90 degrees to become aircraft, become airplane. Okay, that's the design. But this design is dangerous when you transform from a helicopter mode to become airplane mode, and that transformation is somewhat will cause instability of the aircraft. So you need to do some control for that. That's the purpose for this. So when you fly out, you try to change the angle of your propeller, and not changing that angle become unstable. If you don't control it, then the whole aircraft may become unstable system, and that become very dangerous. So you need a controller for that, and this is just a simulations. So we use our predictive control to do this, and that's I give you some of the sample like this. So this is our desired raw responses. This is our desired output. See, you look at this desired output, you cannot never be able to get exact like a desired output because you somehow like you do have some discontinuity here. And this sharp angle, the aircraft cannot do that sharp angle. But the aircraft can do like this, very smooth, and this very smooth response, that's close to your desired shape. So some of the desired responses is not feasible in the sense that you won't be able to reach your desired response. But so your actual response just is as close as possible to your desired response. That's all you can have. So that's what happened here. And this is the control input like that. Okay, that's just some of the example I'm going to show you. This is another model, but this model, the same thing. We have, this is control. Well, let me show you your pictures later, and then you will see what happens. In the early time, before year 2000, that we used two notebooks. One notebook performs system ID and compute. Then one notebook will perform collect all the data, perform system ID, compute alpha and beta, and then one computer will identify the parameter alpha C and beta C, and then to do the controller, and then give the alpha C, beta C to the first computer, and then they will do the control. So this is early time, but now we don't need to do that. Only one processor will be good enough to do it. Okay, now this is real experimental data. Our requirement is we have to turn on our controller after 1 second. So we have only 1 second to work on the system ID and compute the control parameters. That means from here to there we have only 1 second to do it. So from here to there, we have 1 second to do it. And after 1 second, after we have 1 second of that, then we turn on our controller, and that's our responses. And this red line here is our command angles. That's our control input. So the red line is our control input, and this is our final responses. Now you can see that our responses is very small. We still have a control input there because we have disturbances. We still have disturbances. Let me show you some of the real. Okay, now this one. I will spend some time to explain this chart because there's a movie here. I can show you the movie for this. Let's see. Okay, I have a movie here. Then after that I explain to you. Okay. Let's just turn on this line. Movie here. Okay, let's do it. You watch carefully about this. Oops. It works a lot. This is really slow computer. Let's see. Turn off first, and let's do it again. Because it works. Okay, now you look at it carefully here. I'm going to prepare it for you. Alright, look at that. Oops. Okay, you pray again, you watch carefully. Watch this propeller is getting faster, the rotating speed is getting faster and faster and faster. At about 750 RPM, then they start oscillating with the wind. Okay, that's because your rotating speed from 0 and up to about 750 RPM, then they will oscillate with the wind. And then it will be dangerous if you have no control. So we have to have a control to avoid these oscillations between the speed, rotational speed, the propeller speed, and the flexibility of the wing. So that means if you look at carefully from this chart, let me show the chart here. This computer sucks, you know. Keep turn on the screen, turn off my screen here. All right, this is RPM. When this RPM and without GPC, there's one mode, the damping is less and less 1 RPM when this, like this fan, when that fan's the speed is increasing, it's getting faster, faster, faster. And there's one eigenvalue, the damping of that eigenvalue is become the less and less and less up to 750. That eigenvalue damping becomes 0. So no damping at all. If no damping at all means the system will become oscillating with the flexibility of the wing. So if you cross this line, means 0 damping, cross this line become negative damping, that the whole system become unstable. So if you don't do any control of this spinning, then if you can see that they oscillate with the wind, that the amplitude, oscillation amplitude getting larger and larger, it will break the wing. And it will break one of these the setup. And that setup cost $500,000 US. So you are not careful enough, then your $500,000 US is gone. So now here, from 0 to about 600 RPM, that's the time we do this. We get the data, all right? Then we compute this. Then we also compute that. So then at about 600 RPM, we turn on the controller. As soon as we turn on the controller, our damping will jump to 3%. Then come down to 750, our damping still have a 2%. So we are stable. In this region, we are stable. As long as we don't cross this line, the zero damping line, then the system is stable. So this just show you that the same thing as that one, almost like this one, that it keep rotating and rotating, and then we have to do some control. That spinning, this spinning is the disturbances. So that spinning, you consider that as the disturbances. And the way we control the propeller angle. You know, the propeller, this, for example, this is propeller angle. We control the propeller angle. Now, if you control the angle, then you will be able to control the whole system. That means your spinning maybe like this. Then we control this, control that propeller angles. That's the way we do the control. And so you control that propeller angle, it will be able to avoid the oscillating between this propeller and the wing flexibility. That's what happens here. So, and this is real experiments. And this is video funded by Matthew. So if you are interested in looking at this. Okay. Then that's the example, and then after that, there's a lot of applications, like these acoustic applications. How can we reduce the acoustic noises induced by aerodynamics? This is the wind tunnel. So you go to wind tunnel, and wind tunnel provide a wind, strong wind. That strong wind will be our disturbances. And can we reduce the noise introduced by the aerodynamics, by the wind? That's what happened here. Okay, and if you look at this, because this is wind tunnel, and this is the plate outside the wind tunnel. So the wind tunnel will excite the plate, and that plate will make noises. Right? And so we use like a piezo ceramic to control it, and this is one piece, two pieces, three pieces, and this is our input. This is really our input. And the output is just stick on the accelerations. So there's it's not really clear this picture here. And that is the controller. So we have the piezo ceramic, and the real accelerations, and this is accelerations, distributed acceleration, and this is the controller ceramic. And this is the way we do the acoustic noise reductions. And this is just the modes of the plate, just like the fuselage of the aircraft. The plate is just like the fuselage of the aircraft structures. So that aircraft, we control the aircraft structural vibrations. That will reduce the noise, because all the noise inside the aircraft, basically from that the vibration of the fuselage and induced by aerodynamics. That's what happens. So now from here you can see that this is Mach 0.1, Mach 0.2, and the dash line is 0.1, the solid is 0.2, and this is the test structures. And this is the system ID with those without control. So when we do system ID, this is the system ID. And this is the spectrum, input, output, the co-trace functions. So our system ID match this, because you have to match that. This has to be accurate, and this can be accurate, and then this can be good. If this is not accurate, you won't get good result of this, and you won't get good result of that. Okay, that's what happened here. Okay, no control. With no control, then this is what happens here. Alright, this is controller performs. If you are control, then this peak can be control coming down. Okay, and this is then there are some experiments that doing in 1998. That's high-speed wind tunnel. This is supersonic. So you can this Mach 0.8. We can reduce above 9 dB with the control, the blue line. And this 2.5 Mach, that's supersonic. And then you can reduce up to about 9 dB noise reductions. So that means very good, because our requirement is only 5 dB. The Air Force gives us only 5 dB, and we give them 9 dB. So that's even much better. We are almost double the requirement. And this is, we can go up to 9.3 dB reduction, noise reduction. The noise reduction means the peak is almost gone. The peak, this peak almost gone. And this is all come from the aerodynamics disturbances. Well, there's too much things going on here, so I'm going to just give you a little conclusion here. That will end up our semester. Okay, now in here we learn how to design a GPC controller. And also show you that the theoretical development and give you numerical simulations and experimental investigations. And all the results show that at this moment the GPC works quite well. And so that NASA, the Air Force still use GPC for their controller design at this moment, particularly for unknown disturbances involved to the system. That's what happens. Okay. But anyway, I think that's all we got for predictive control, and I didn't have much chance to explain all the experimental results, because that's a lot of things involved in there, and also requires some system ID background. That's what happens. So I didn't spend much time to explain to it. Do you have any questions? No? Yes? Any question about the final exam? Any question about anything? Well, maybe just write it down so you know that, what you expect the final exam. So I just say here's a possibility. I'm still thinking about that. 60% yes or no. And 40% other say calculation problem. Okay, I say there's a possibility. And so I let you prepare for it. And again, this is an open book. Notes, open notes. All right. And what else? Any other questions? If you do your own homework, you will be able to solve the problems and all the concept here. And yes or no problem. That's really most of them are wrote on the whiteboard. If you write good notes, what you going to get all this, and we will cover. We'll cover the ball placement, optimal control, and delivery control. Okay, anything else? No? You know? No, if not, thank you for taking my class. I hope you enjoy it. Take it easy on your final exam. And don't think too much. Sometimes you think too much and you make your problem more complicated. All the problem is simple. Alright, then just end of the class. Thank you again. Bye.